This week's tutorial questions involve proofs by equality and proofs by induction. And now, because these proofs get quite complicated, I thought the best thing to do would be for me to go through the first couple of proofs in the video to show you how they're done, and then you can follow along by yourself, and then you should be able to do the rest of the proofs on your own. So, the way the proof system has been upgraded now is, for these proofs by equality, is to add a new reflexivity command, which can be used when the goal is t equals t for any t, to prove that every term is equal to itself. So this allows us to prove equalities. And also we have the two rewrite commands, to rewrite left to right and right to left, which can be used when the formula in focus is an equality, t1 equals t2, and the left to right one rewrites every occurrence of t1 in the goal to t2, and the right to left one rewrites every occurrence of t1 to t2. Almost always we'll use the left to right one because that's the way things are set up. Now let's have a look at the proofs for equality. So a lot of the time when we do proofs for equality, we're going to assume some axioms about what things are equal. So question 3 in these proofs assumes that the two addition axioms from the induction video hold, and questions 4, 5 and 6 assume that these abelian group axioms about combining things hold. But let's first look at the first two pure equality proofs. So the first one is symmetry. It says that for all x and for all y, if x equals y, then y equals x. So let's see how to prove this using our new proof rules. So because we're proving a for all, the first thing we do is introduce the variables in the for all. And then we introduce our assumption that x equals y. So we introduce x equals y. Now what we want to do is use this assumption that x equals y to rewrite our goal. So what we're going to do is rewrite the x here to y in the goal, because x equals y. And then we'll have the goal is y equals y, and we can prove that using reflexivity. So we use x is equal to y. So now the focus is that x is equal to y and the goal is y equals x. And then we rewrite left to right. So that means we rewrite all x's to y. So now the goal will be y equals y. Now the goal is y equals y, and then we can prove it using reflexivity. And that completes the proof. So to prove this one, we take the goal, we rewrite it using our assumption, so rewrite all the x's to y's to get y equals y, and then that's true by reflexivity. And the proof tree just follows this exactly. It's quite a linear proof. The next thing we're going to prove is transitivity, which is another pure property of just equality. And this says for all x, y and z, if x is equal to y and y is equal to z, then x is equal to z. So you could think of this as plugging two equalities together if they have a common endpoint. So again, first we have to introduce all the variables. So we introduce x, y, and z. And then our two assumptions, the fact that x equals y, and the fact that y equals z. Now our strategy is to rewrite our goal using these assumptions. So what we're going to do is use the assumption that x equals y to rewrite the goal from x equals z to y equals z. So that is, we rewrite this x to a y. So we use x is equal to y. Then we rewrite from left to right to get y equals z. Now y equals z is our second assumption. So we can now prove this by using y equals z. Now the focus is the same as the goal, so we're done. We didn't have to say done here. We could have used the fact that y equals z to rewrite the goal again. So let's see how that works. We've got y equals z in our focus, and the goal is y equals z. so we can rewrite the y to be z. So we can do rewrite left to right. Now the goal is z equals z, and that's an instance of reflexivity. So again, we have quite a linear proof. We do some introductions, then we use the fact that x equals y to rewrite, we use the fact that y equals z to rewrite, and then finally we've collapsed it down to the fact that the thing we want to prove is z equals z. The third question asks you to do some computation using the add axioms. So the add axioms are the fact that adding 0 to x is equal to x, and adding the successor of x to y is the same as taking the successor of adding x to y. And the goal is to prove that 2 plus 2 is equal to 4. And we're going to do this by successively applying the axioms over and over again to rewrite this the term on the left so it becomes equal to the term on the right, and then we'll be able to use reflexivity. So let's see how this works. So our goal is to prove that add a successor of 0 to 2 is equal to 4. And what we're going to do is match against add s, so that's adds with a successor in the inside, so we've got a successor here, and effectively moves the successor symbol to the outside. So we're going to use add s, and now to match the add s, or the left-hand side of it, with the goal, we want to give an x such that it matches this. So the x is going to have to be successor of 0. Oh, successor of 0. And now we have to instantiate the y. So we're going to instantiate with 2, successor of 0. And now we've got an equality in focus which matches the left-hand side of this equality. So then we can use that to rewrite left to right. So now what we're trying to prove is the successor of adding 1 to 2 is equal to 4. So we're going to use add s again to get this s on the outside of the add. So then we instantiate this with 0 this time, and y is now going to be 2 again. Now again, we've got an equality where adding 1 to 2 is equal to the successor of adding 0 to 2, and the thing on the left-hand side of that equality matches this part of the term in here. So we'll be able to do a rewrite left to right. Now we've got a successor of adding 0 to 2 is equal to 4 is our goal. Now we want to use the add 0 axiom, which says that adding 0 to something gives us the thing. So then it will get rid of this add 0 part here, and we'll end up with 4 successors in a row, then 0, which is the same as the right-hand side. So now we need to give it the thing which is left alone by adding 0, so instantiate that with 2, so successor of 0, and rewrite from left to right. So now we've got a goal which says that 4 is equal to 4. So we can prove that goal using reflexivity. So you can see here that the way this proof worked was by successively applying one of these two axioms. First we had to apply add s twice to add 2, and then add 0 to do the final adding 0 onto the second part. Ultimately, the proof ends with reflexivity, where we get down to a place where the thing we want to prove, the goal we have to prove is just that one thing is equal to itself. The fourth equality proof is slightly more complex. So here we have a whole bunch of axioms about some operation called combine and an operation called inverse, and a constant called emp. And the idea is that we can think of combine as being a bit like addition on the integers. And these are some properties that addition on the integers satisfies. So one is that if we add x, y, and z, then it doesn't matter what order we do it in. We can add the y and z first and then add x onto it, or we can add the x and y first and then add the z onto it later. Also, it doesn't matter which way round we add things. We can add x and y, or y and x, and they're the same. Also, for the integers, that is includes negative numbers, for every number it has a negative number, and when we add those together we get the empty number, or 0. And also, if we add any number to the empty number, we get back to where we started. So you can think of this as 0. And now the goal is to prove this property, that combining or adding x, 0 and y is the same as just adding x and y. And now this isn't entirely straightforward because we've got this combining empty thing here, but the emp and the x are in a different order. So we can't immediately just use adding x to emp gives us x and instantiate it with y, because the emp and the x are in the emp and the value are in the wrong order. So there's two ways of proceeding. One way is to use associativity to move the brackets here so that we're combining x and emp first and then combining y. And then we can use our combine emp axiom, or we can use commutativity to switch the order of emp and y and then use the combine emp axiom. Let's see the version which uses associativity. So first we're going to introduce the variables x and y. And now what we're going to do is rewrite using associativity. So this is going to rewrite this combine x emp y. We're going to get x emp y to having the combine on the left instead. So we use combine ASOC, which is the name of the axiom, and then we instantiate it with x emp and y. And now it's a bit difficult to see here because I've zoomed in so much, but we've got combine x with combine emp y is equal to combine x emp combined with y. And we can see that the left-hand side here is the same as the left-hand side here. So now that means that we can rewrite. And the goal now is to prove that combine x and emp with y is the same as combine xy. And now notice here, this combine x and emp matches the structure of the combine emp axiom. So we can use combine emp, instantiate that with x, and now we've got combine x emp is equal to x. So this means we can rewrite this part of the goal to x, and we get the goal is to prove that combine xy is equal to combine xy, which we can prove by reflexivity. So this has shown you 4 proofs using equality, and there are now 2 more proofs for you to do by yourself that we'll cover in the tutorial on Friday and Monday.